Hello everyone and welcome to lecture 11 of pre-calculus algebra. Yeah, we finally got over lecture 10. And today we're going to talk about the graph of an equation and the story it tells. And specifically, we're interested in the graphs of equations where the equation defines y as a function of x. We're interested in equations where the equation defines a function from set x, the domain, to set y, the range. So first order of business, given a graph of an equation, can we determine whether the equation defines y as a function of x? In other words, can we determine whether the equation defines a function from the domain x to the set y? That's our first order of business, and we might already know the answer to this question because we talked about it in lecture 10. But just for the sake of reinforcement, we're going to talk about it a little more right now. Okay, here are our first few examples. We're going to do maybe 3 more after this, maybe even more than that. Determine which graphs below define y as a function of x. And believe it or not, that's the same thing as saying determine which graphs below define a function from the domain x to the range y. If we have a function from the domain set x to the range set y, we say that it defines y as a function of x. It's a little bit awkward, but that's the way it's done. Well, how do we just look at the graph of an equation? See, we don't even have the equation written here. How are we supposed to determine whether this graph represents y as a function of x? If we did have the equation here, it might be helpful, maybe not, but we don't have the equation here. We just have the graph. So how on earth, just looking at the graph, are we supposed to figure out whether this graph represents y as a function of x? You may remember that we did something in lecture 10, part 1 or part 2 or part 3. It's in there somewhere. But you might remember that we did something called the vertical line test. And we want to remember that. What does the vertical line test tell us? The graph of an equation represents a function exactly when it is not possible to draw a vertical line that intersects the graph in more than one place. If we can draw a vertical line that intersects the graph in more than one place, like right here and right here, then we don't have a function. And here's the reason why. This is a vertical line, so all of the x coordinates on this vertical line are the same. And we'll call this x of 1, a particular x value. Well, x of 1 is the x coordinate of this point, and it has some y coordinate, y sub 1, up here. Well, let's see. This point of intersection is on the vertical line also. So x1 is the x-coordinate of this point of intersection. But the y-coordinates are different. Look at that. We'll call this y-coordinate y2. The fact that this vertical line intersects the graph of the equation at more than one point indicates that this one x value is assigned more than one y value. The vertical line intersects the graph in more than one place, not a function. As a matter of fact, things even get worse over here, don't they? Holy moly, we can draw a vertical line that intersects the graph in 4 places. Now, as long as the vertical line, as long as any vertical line intersects the graph in more than one place, we ain't got a function. Now let's apply that same criterion to this graph. Can I draw a vertical line that intersects this graph at more than one point? Let me try. I'll draw a vertical line here. I'll draw a vertical line there. I'll draw a vertical line there. So far, every vertical line only intersects the graph at one point, and it doesn't change. 1 point, 1 point. No matter where we draw a vertical line, it doesn't intersect the graph at more than 1 point. No matter where I drew the vertical lines, they only intersected the graph at 1 point. This is a function. Now let's apply that same criterion to the next graph. Draw vertical lines, intersects at 1 point, vertical line, 1 point, vertical line, 1 point, vertical line, intersects at 1 point, vertical line, intersects at 1 point. No matter where we draw a vertical line in the xy plane, it doesn't intersect the graph at more than 1 point. So this thing is a function. And all of these things we applied the vertical line test. If we can draw a vertical line through the graph of an equation, and the vertical line intersects the graph of the equation at 2 or more points, more than 1 point, the graph does not relate x, does not express y as a function of x. If we can draw vertical lines anywhere in the xy plane, And those vertical lines never intersect the graph of the function at more than 1 point. See, this line, 1 point, this line, 1 point, this line, 1 point. If we can't draw a vertical line that intersects the graph at more than 1 point, it's a function. If every vertical line intersects at most at 1 point, it's a function. Same thing here. If every vertical line intersects the graph at most 1 point, it's a function. As a matter of fact, maybe I can be a little bit more precise. If a vertical line intersects the graph at exactly 1 point, it's a function. Now, if the vertical line doesn't intersect the graph, does that mean it's not a function? No, it doesn't necessarily mean that. But if it's impossible for us to draw a vertical line that intersects the graph of the function at more than 1 point, it ain't a function. So you just remember this guy. This vertical line intersected at 2 points. We don't have to go any further. This thing is not a function. Three more examples, everybody. And in each case, we want to decide whether the graph defines y as a function of x. In other words, does this graph define a function from set x, the domain, to set y, the range? And what's our determining criterion? The vertical line test. Let's see if we can draw a vertical line that intersects the graph at more than 1 point. Oh, this one's easy. Just like drawing candy from a baby. 2 points of intersection. This vertical line intersects the graph at more than 1 point. So what do you say? Not a function, right? Now, what about this thing? I guess we call this an ellipse. Does the graph define y as a function of x, or does the graph define a function from set x, the domain, to set y, the range? Let's see. Vertical line test. Can I draw a line that intersects the graph at more than 1 point? Sure I can. There's a vertical line. It intersects the graph at more than 1 point. Not a function. And finally, this guy. Does this graph define y as a function of x? Does this graph define a function from set x, the domain, to set y, the range? Let's draw our vertical lines. 1 point of intersection. 1 point of intersection. 1 point of intersection. And we see how this is going to play out. No vertical line that we can draw intersects the graph of this equation at more than 1 point, so this graph defines y as a function of x. Now, I guess there's one more graph that I want us to see, just to cover a situation that we haven't seen yet. here are a couple of examples that may give us some vexing moments trying to figure out whether the graph actually defines y as a function of x. Well, my weapon here is the vertical line test. And I draw vertical lines right here. And in each case, one point of intersection, no more. Now notice as this graph heads toward the y-axis, it starts to go down at a really steep angle. As this graph goes down, it gets closer and closer and closer to the y-axis, but it never gets there. So this graph never actually touches the y-axis. And this graph never goes beyond the y-axis over here. So, I can draw a vertical line here that doesn't intersect the graph at all. Does that disqualify the equation of this graph from being a function? Or does that mean that this graph does not relate y of x? I'm sorry, this graph, does it mean that this graph does not define y as a function of x? No. The only thing that it really means is that the y-coordinate of this line, the x-coordinate of this line, x equals 0, and all of the x-coordinates to the left of this line just aren't in the domain of the function x. I can't draw a vertical line anywhere here that intersects the graph of this graph at more than one point. So this baby is a function. Well, we draw a line over here and it doesn't intersect the graph anywhere. That's okay. That doesn't mean that this graph does not define y as a function of x. What it does mean let's see, I'll write this in interval form. What it does mean is that only x values in this interval are part of the domain. Only x values that are positive real numbers are part of the domain. Now we have a similar situation over here. I draw my vertical lines, one point of intersection. I draw another vertical line, one point of intersection, one point of intersection. And over here, I draw a vertical line, one point of intersection, a vertical line, one point of intersection, one point of intersection. All of the vertical lines that I've drawn intersect the graph of that function at exactly one point. But suppose I do this. Suppose I get sneaky and I decide to draw a vertical line right here. Well, you know what? This vertical line doesn't intersect the graph at any point. So does that mean that this graph doesn't define y as a function of x? No, it doesn't mean that. All it means is that there are some real numbers that are not part of the domain of the function. There are some real numbers that x cannot be equal to. So over here I'll write domain. Let's see, before I write that, I'll write is a function. And then after that, I'll write what the domain is. The domain is the set of all real numbers over here that are less than -1. So that's the interval from -infinity to -1. And all of the x values that are to the right of x equal +1. The positive x values that are greater than 1. That's the interval 1 to infinity. So what does that mean? The x values in the closed interval from -1 to 1 are not part of the domain. So that explains why we can draw a vertical line here between x equal -1 and x equal +1 that doesn't intersect the graph. The fact that I can draw a vertical line between x equal -1 and x equal +1 that doesn't intersect the graph means that the real numbers between -1 and +1 on the x-axis are not part of the domain. The fact that I can draw a vertical line here that doesn't intersect the x-axis, that doesn't intersect the graph rather. The fact that I can draw a vertical line here that doesn't intersect the graph doesn't mean that this graph does not define y as a function of x. This graph does define y as a function of x. A new example. Getting information from the graph of a function. So this graph represents a function, f of x. And remember from lecture 10, when we have a function, we use y and f of x interchangeably. So f of x, that's the same thing as y and vice versa. Now, I've already said this is the graph of a function. How did I know that? I'm not going to draw anything here, but if I were trying to determine whether or not this graph defined y as a function of x, what would I do? I'd draw a bunch of vertical lines, right? And if it were possible to draw a vertical line that would intersect the graph at more than one point, it's not a function. But if every vertical line that intersects the graph intersects at exactly one point, then it's a function. And if I have vertical lines that don't intersect the graph, it doesn't mean anything other than the x value associated with that vertical line is not part of the domain. So let's see. This is a function. I can't draw a vertical line that will intersect this graph at more than one point, so it is a function. Now, what questions can I ask about this? We'll just look at some easy points on the graph to identify. This one seems like a really easy one to identify. And when x is -1, it looks like y is +1. And when x is -2, it looks like y is 4. So let's see, -2, 4, -1, 1, 0, 0. So I'll write those down. -2, 4, -1 and +1, 0, 0, And do we have more? Yeah, let's see. Here's a point, and it looks like it corresponds to x equal positive 1, y equal positive 1. And we'll do one more. What about this one up here? Whoops. Excuse me, 2, you just moved. Okay, when x is 2, y is 4, that's another point on the graph. So we've named 5 points on the graph. And remember, as far as ordered pairs go, the second number of an ordered pair represents the y coordinate. But y and f of x are the same thing. So let's see. We could say that this is x equal negative 2, y equal f evaluated at negative 2, which is 4. Here we could say x equals negative 1. And this corresponds, this is the y coordinate, y equals f evaluated at negative 1, which is 1. And what about this point? This represents x equals 0, and this represents y equals f of 0, which is 0. For this point, x equals 1. And here, y equals f evaluated at 1, which is also 1. And finally, we'll look at this point. X equals 2. And y is the same as f of x. So this is f evaluated at the x coordinate 2. And that turns out to be 4. Okay, goody. We named some points on the graph. The domain. From this graph, it may be hard to tell what the domain is, but suppose that I zoom out and show what the graph looks like. I'm going to zoom out, and when I zoom out, this is what the graph looks like. So it looks like the graph goes to the right all the way to infinity. It looks like the graph goes to the left all the way to infinity. So the domain is the set of all real numbers from negative infinity to positive infinity, that interval. And what about the range of the function? That's the set of all y values. Let's go back to this graph for a good answer. The lowest point on the graph is right here. And right at this point, y equals what? Y equals 0. As a matter of fact, this graph actually sits on the x-axis. And every point on the x-axis has a y coordinate of 0. So this graph actually does attain a y value of 0 right here at this point. But does the graph ever dip below the x-axis? And down here below the x-axis, that's where y is negative. Since the graph doesn't go below the x-axis, y is never negative. Y does equal 0 though, and it seems like if we follow this graph in the Y direction, it goes straight up to infinity. So it looks like the set of Y values is all positive real numbers plus 0. And the set of positive Y values, that's the range. I'm sorry, the set of all Y values that are on this graph, that's the range. Y can be 0, and Y can be any positive number. Now let's see, what other questions can we answer? Y-intercept. Where does this graph intersect the y-axis? Son of a gun, right here at 0. The y-intercept is 0, y equals 0. And think about it. When a graph intersects the y-axis, what's the x-coordinate? The x-coordinate of any point on the y-axis is what? 0. So the y-intercept, we could say, is y equals 0. Or we could say the point 0, 0. Now what about the x-intercept? Well, this graph intersects the x-axis at one point, right at x equals 0. But what is the y-coordinate of any point on the x-axis? Isn't the x-axis the set of all points where y equals 0? So we could say that the x-intercept is x equals 0. That's where it intersects the x-axis. We could also say that it's the point x equals 0, y equals 0. Now let's ask some more questions. We already know for what x values f of x is equal to 0. And by the way, maybe I should clarify this. Y equals 0, that's the same as f of x equals 0. We know where f of x equals 0. Y equals f of x is 0 when x is 0. For what x values is f of x greater than 0? Well, you know what? The region in the xy plane where y is greater than 0 is the entire section of the plane that lies above the x-axis. So anywhere above the x-axis, y is greater than 0. And you know what? To my way of thinking, y is greater than 0, 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 y is greater than 0. All of those points are above the x-axis. So on each of these points, y is greater than 0. And I can do the same thing over here. This point's above the x-axis, so y is greater than 0. This point's above the x-axis, so y is greater than 0. This point is above the x-axis, so y is greater than 0. And y is greater than 0 here, and y is greater than 0 here. So for all of these points, y or f of x is greater than 0. As a matter of fact, it looks like the only place on the graph where y isn't greater than 0 is right there, where y equals 0. When x is 0, y is 0. But for all other values of x, f of x or y is positive. So for what x values is f of x greater than 0? And by the way, remember f of x and y, they're the same thing. And f of x or y is greater than 0 for all values of x except x equals 0. In interval notation, I'll write it this way. These round parentheses mean that 0 is not part of the interval. So all values of x less than 0 and all values of x greater than 0 are values so that f of x is greater than 0. Now let's look at this. For what values of x is f of x less than 0? Now we've kind of already answered this in an indirect way. Let's answer it more directly. Where is y or f of x less than 0 in the plane? Isn't y less than 0 below the x-axis? So the place in the xy plane where f of x is less than 0, is that part of the xy plane where the graph of f of x dips down below the x-axis? Tell me something. Do you see the graph of this function dipping below the x-axis? I sure don't. This graph lies either on the x-axis at that point or above the x-axis at all other points. At no time does this graph actually go below the x-axis. So for what x values is f of x less than 0? None. Well, that was kind of fun. Let's do some more. Okay, we're back with another one. What can we gather from the graph of this function? And yes, it is a function. If we draw vertical lines, no vertical line is going to intersect that graph in more than one point. So we've got ourselves a function here. And the first order of business is, what are some of the points on the graph? Well, let's see. This is one right here. And here, let's see, x is 2. So y is 0 because it's on the x-axis. Here, x is negative 2. And y is 0 because it's a point on the x-axis. And I guess that'll do for now. Negative 2, 0. 0, 4. And 2, 0. this is the x-coordinate, x equal -2. And this is the y-coordinate, but y is exactly the same thing as f of x. So I'm going to put that this is f of -2 equals 0. Here's another point. This is the x-coordinate. X is 0. And this is the y-coordinate. But again, since y and f of x are the same thing, I'm going to write this as f evaluated at x, which is 0. And that's equal to 4. And one more point to investigate. This is the x-coordinate, and this is the y-coordinate. But again, since y and f of x are the same thing, I'll write this as f evaluated at the x-coordinate 2, and that's equal to 0. Okay, so I named some points on the graph. And I know that f of -2 is equal to 0. F evaluated at 0 is 4. F evaluated at 2 is 0. Oh, now the domain. This graph sort of looks like it's going to take off in that direction without bound. Let me zoom out again. If I zoom out, I'll see that this is what the graph looks like. And so this graph will continue to go down and go to the right. This part of the graph will continue to go down and continue to go to the right. So I'm going to say that the domain is the entire set of real numbers from -infinity to +infinity. And let me get my numbering straight. A, B, domain. Range, okay. This is the set of all y values. And notice that the graph goes below the x-axis and keeps on going. So I'm thinking that the y values are going to go all the way to -infinity. But what's the greatest value that y assumes? 4. Y is never greater than 4. So I'm going to say that the range is this, -infinity to 4. Okay, intercepts, we got a few. And I'm going to say, what? Y-intercepts first. Here we intersect the y-axis at y equal 4. So I'll say y equal 4. Or I could denote that this is the point 0, 4. And since this is the y-coordinate, this is our function f evaluated at the x-coordinate. And another way that we could write this as 0, f of 0 equals 0, 4. That's the y-coordinate. So any of these ways are fine. What about x-intercepts? Well, we got one right here, don't we? It crosses the x-axis at -2. And we got another one crosses the x-axis at positive 2. So I could say x equals negative 2 and x equals positive 2. Or I could give both the x and y coordinates, couldn't I? And I could say negative 2, 0. And positive 2, 0. And maybe that's enough. This seems to be a bit cumbersome. Values of x such that f of x is greater than 0. Let's see, f. So which values of x, or for which values of x, is f of x greater than 0? Well, wherever f of x is greater than 0, the graph is above the y-axis. And the graph is above the y-axis between x equal negative 2 and x equal positive 2. And let me do a quick check here. I said x is between negative 2 and positive 2. Should I include x equal negative 2 and x equal positive 2 here and do that? Or should I just leave it the way that it was? Let's see. When x is negative 2, this point is on the x-axis, so x is not greater than 0. X is equal to 0 here, isn't it? So I don't need this to be x greater than or equal to negative 2. I just need x greater than negative 2. If x is equal to negative 2, then f of x is 0, and that's not positive. That's not greater than 0. The same thing here. If x is equal to 2, then f of x is 0. And we're looking for x values where f of x is greater than 0. So the x values for where f of x is greater than 0 are all the x values where this graph lies above the x-axis. And shame on me, I should have labeled my axes. Now, for which values of x is f of x less than 0? Well, the graph of f of x, maybe I should say it this way. F of x is less than 0 wherever the graph of f of x goes below the x-axis. So that would be any x value to the right of this point. For any x value to the right of this point, f of x is less than 0. So I'd say x greater than 2. And for any x value to the left of this point, the graph is negative, or f of x is negative, because the graph dips below the x-axis. So any x value to the left of this point will make f of x less than 0. So I'll write x greater than negative 2. And in interval notation, I'd write it this way. x less than -2, x greater than +2. Okay, let's see what else we need to look at. You know what? I think we're going to call it a wrap on this lecture.